I've already introduced all of the techniques we need in order to analyze circuits containing ideal sources and resistors. However, direct application of KVL, KCL, and Ohm's law can be labor-intensive. In the next few chapters, I'll be talking about techniques that allow us to simplify our analysis. The first of these techniques is called circuit reduction, which I'll introduce in this video. So far, we've used a brute force technique which requires us to define all possible voltages and currents in all of the resistors in a circuit. This is called the exhaustive approach and results in a large number of unknowns and a correspondingly large number of equations that have to be solved to calculate the unknowns. However, we often don't need to determine values for all possible variables in a circuit. Usually we need to calculate only a few variables that are of interest in the problem at hand. If we're only interested in a few variables, it would be nice if we could write and solve fewer equations and determine just the variables we need to know. One such shortcut approach is circuit reduction. The goal of circuit reduction is to reduce the number of equations that we need to write and solve. The basic idea is that we're going to reduce the number of elements in the circuit by combining multiple circuit elements into a single element with the same voltage current characteristic as the original elements. If we reduce the number of circuit elements, we automatically reduce the number of unknowns that we have in the circuit. It's important to keep in mind that this is an analysis technique rather than a modification to the original physical circuit. We're just conceptually changing the circuit to make our calculations easier. Not all circuit elements can be combined, so be careful when you're reducing your circuit. You can only combine resistors if they are either in series or in parallel. Circuit elements are in series if they share the same current. So if I have two and only two elements connected at a single node, KCL at this node will tell me that these currents, I1 and I2, are the same. If I have more than two elements connected at this node, they won't be in series. Circuit elements are in parallel if they share the same voltage difference. If I do KVL around a loop and encounter two and only two elements in the loop, those elements will be in parallel. I want to emphasize that not all elements are either in series or parallel. Many combinations of elements can't be reduced. Identification of series and parallel elements is an important point. Now let's take a look at how identifying series circuit elements can help us reduce the number of unknowns in our circuit analysis. These elements are all in series. I can tell that by doing KCL at any of these nodes. There's no place else for the current to go, so all of these share the same current. I only need one current variable. So if this current is I, then this current is I, this current is I, this current is I, and this current is I. I've actually written 5 equations and 5 unknowns, solved them in my head, and reduced it to a single variable. Now if this current is I, the voltage across this resistor by Ohm's law will be R1 times I. This voltage will be R2 times I, R3 times I, and R4 times I. Now I've written Ohm's law 4 times. The only thing left to do is KVL. So KVL says minus V sub S plus this voltage, R1 times I, plus this voltage, R2 times I, plus R3 times I, plus R4 times I is equal to 0. That gives me one equation and only one unknown. I can solve that for I. Once I have I can find out anything else about this circuit that I need to know. Now let's do an example of parallel circuit elements and how we can use that configuration to reduce the amount of effort we need to do. If I call the voltage across this current source V sub S and then do KVL around any of these loops, I find out that these resistors all share the same voltage difference and they're all V sub S. Now if I define the currents through these resistors, say this is I1, this is I2, and this is I3, by Ohm's law, I1 is equal to V sub S over R1. I2 is V sub S over R2, and I3 is V sub S over R3. I can do pretty much all of this in my head. Now, if I do KCL up here, with positive currents leaving the node, this is going to be minus I sub s plus I1, which is V sub s over R1, plus I2, which is V sub s over R2, plus I3, which is V sub s over R3. That gives me fairly easily one equation and one unknown, which I can solve for V sub s. Once I know this voltage, I can find out anything else I need to know about this circuit. In the remaining videos in this chapter, I'll give more details about how circuit reduction can be used to simplify our analysis of electrical circuits.